Okay, so it has started, right? So now, given that we have seen these things, right? What is the next step? Uh, so this is 06. So now what we are going to see is something which is even more generic. Okay. So basically, we are going towards something called diffusion models. Okay. However, we'll start a little from something which is just an extension of VAs, and we'll see how it progresses. Okay. So this was VAs, right? Yeah. So now we are going to see this lecture is something called hierarchical VAs. Okay. Hierarchical VAs. Okay. We'll see what this thing is. Okay. So just maybe uh, okay. So I am taking this content from so this is these are some lecture notes from I'll mention that so that if you want you can go back and refer to it. So this is taken from understanding diffusion models by Calvin Lowe. So I'm taking this stuff from his lecture notes. Okay. So if you want, you can go back and look at these notes. Okay, so let's start. So, okay. So in VAs, what we have seen is there are two things. So there are two views. There is Z, there is X. There is a inference view and there is a generative view, right? So the inference view is something like this, which asks for a distribution Q phi Z given X. And there is a generative view which using which you can generate data, which is given by something called p theta x given z, something like that, right? What you can do is you can generalize this thing. What do I mean by generalizing this thing? Uh, Actually, I should have written it the other way so that it becomes easier. Let me write it. So let me write it in the some other way and just reverse it. Let me write x here, z here. There is a inference view. Uh, there is a this is the generative view which takes z and gives you x, and then there is a inference view which takes x and gives you z. This is how VAs look like, right? This is how VAs look like. So what you can do is you can actually generalize this thing. Instead of having a single latent variable, you can have multiple latent variable which depend on each other. What do I mean by that? So let me show it to you. So which is what we will call HVAs, which is hierarchical VAs. So hierarchical VAs, these will have X, okay? There will be multiple latent variables Z1, Z2, maybe Z3, so on till ZT, okay? And similar to what we have in VAs, each previous latent, so something like this. So Z1, okay, will depend only on Z2. So this will be the generative view for Z1. Okay, there will be P of Z1 given Z2. In VAs, we had just this thing, right? We had only P of X given Z1. But now we have multiple latent and each latent depends on its previous latent. Z2 similarly depends on Z3. So this has another generative view, PZ3 given, sorry, P of Z2 given Z3. Similarly, ZT will generate something, have a generative view for for its previous latent, which is P of ZT minus 1 given ZT. ZT itself will be some distribution, some easy distribution like a Gaussian something. And now we have similar to what we had in VA, right? There was a inference view as well. So what is the inference view? There will be inference view from which you can infer Z1 from X, right? So this will be Q of Z1 given X. You can infer Z2 from Z1. So this will be like Q of Z2 given Z1. This similarly you will have Q of Z3 given Z2. Similarly, you can infer ZT from its previous latent Q of ZT given ZT minus 1, right? So, so this is how it is. I think one way to look at it is that you can think of this box, right? Whatever this box is, whatever is inside this, sorry. Okay. So you can think of whatever it is there inside this box as one. So it's like, yeah. So you can think of it like this, right? So you can think that whatever this one latent variable was in your normal VAE, it is now actually a bunch of other VAs stacked upon each other. That's all. Does that make sense?
Yeah, so I have a query here that I mean here the entire diagram is so very symmetric. So can this be a
Yeah.
complicated case like say Z3? It's quite possible that in the latent space Z3 may depend on the Z2 and the Z7 as well, and that kind of the situation.
Yeah.
And the
So
things are not
that's
very
okay. So
numerical in
yeah, yeah.
nature.
So this is like a Markovian HVAE. Okay. Like this is a Markovian model where you only have latents depending on its previous latent. Okay. But you can construct VAs. So that is a more general PGM. Okay. I mean, if you think about it, that PGM will be a even more generic PGM, which might need like its own sort of analysis, and you can perhaps take the theory from here and try to construct something like that. Yeah,
Okay,
but
okay.
that won't be Markovian. Yes.
Yes, yes, yes.
Yeah.
So even in the Markovian, we can, I mean, go two or three steps back, and then Z3
S-
depends on Z2 as well as on the Z1, and with that kind of the situation.
Sorry,
And
can
while
you
the
repeat? I lost you for a second or two there.
yeah, so my point is that even if this entire thing is Markovian, then instead of going just one step back, I mean, we can think of moving more than one step back and say
Mhm.
Z2 and Z1 as
So
well.
yeah, so that will be like a higher order Markovity, right? That's what you're talking about. So
Yes,
this is
yes,
like
yes.
first order Markovian model. You can have second order, third order Markovian models too. Yeah, possible.
Okay, okay,
That's
yeah,
possible.
fine.
Right. So let's try and see what is it with what happens with these kind of uh, uh, what happens with these kind of models if you want to learn something like this, right? Let's see what happens. So first things first, we need to start with your remember always start with the joint distribution, right? So let's start with P of okay. Uh okay. Uh what can we do? Where should we start from? Okay, it's fine. Let's start with this thing where let's try to write down the forward, I mean, let's try to write down the generative distribution, right? So generative distribution is P of X Z1 to T, right? So you have x and z1 to t. Let's try to write the generative view. So generative view is basically this thing, right? So this thing. Let's try to write this thing down. The distribution of the generative view. So this will be again, since these are all PGMs, right? It's quite easy. So remember PGM, you have P of ZT, then you write down the distribution of ZT minus 1 given ZT because ZT minus 1 only depends on ZT, and similarly so on and so forth, and then write down P of X given Z1. That's all, right? So let's write it down. So that will look like P of ZT. You will have maybe if you have parameterized distribution, this will be P theta of X given Z1, right? So X given Z1, it's this part. Then you have uh, P theta of maybe Z1 given Z2, so on till P theta of ZT minus 1 given ZT, right? Right. This you can also write down as P of ZT, P theta of X given Z1, product of T equal to 2 to capital T, right? P theta of ZT minus 1 given ZT, right? I have simply written down the distribution of the generative view, that's all. Similarly, what is the distribution of the inference view? So the inference view is something like Q phi of Z1 to T given X, right? So this is like in V8, this was Q phi Z given X. So but we have multiple latents, so Z1 to T given X. This will be something like Q phi of Z1 given X in product of T equal to 2 to capital T Q phi of ZT given ZT minus 1. Because I mean it's quite simple, right? Z2 only depends on Z1, so this distribution into Z3 only depends on Z2, so this distribution, so on and so forth. So that's how the inference distribution would look like, right? Now, okay. Uh, now let's start by writing down. So let's see what is the elbow that we'll get, right? I mean, end of the day, we want to maximize our elbow. That's all. So I mean that it will look quite similar, but nonetheless, let's write it down. So what is your? I mean, you will always start with your log likelihood. So it's log px. If you remember, uh, how we started with VAs or in general how we derived elbow, we will follow the same thing, but the only difference is instead of having one Z, we will have like multiple Z. So this will be P of X comma Z1 to T dz1 to T. So this is nothing but multiplying it. So I mean, I hope you can see that this thing is just P of X. So nothing really changes here. Okay. It's just marginalizing out Z1 to T, that's all. Now what we will do is this thing will become log of integral of P x comma Z1 to T, right? Multiply and divide by your variational distribution. So Q phi Z1 to T given X divided by Q phi Z1 to T given X dz1 to T, right? Just multiplying and dividing by same thing, that's all. Uh, Now what you can do is, so this thing is actually nothing but this is log. So this thing inside is actually expectation of what? Expectation of this quantity, right? This quantity right here. So this is P of X comma Z1 to T Q phi of Z1 to T given X, right? And what is this expectation under? The expectation is under this distribution, which is q phi z1 to t given x. It's actually very similar to how we derived the elbow earlier, similar to that. And now you simply apply your Jensen's inequality, right? This thing is greater than or equal to expected value of, so log of expectation is greater than or equal to expectation of log, right? This is q phi z1 to p given x log of p x comma z1 to t divided by q phi z1 to t given x, right? That's all. So this is your elbow now. Uh, so this is your whatever f of q, if you want to call it. This is your elbow for hierarchical V's. And if you see, there is nothing new actually. What was the, so I mean, this, if this is FHVAE, right? What was your FVAE of Q? If you recall, that was nothing but expectation of Q by given X log of P of X comma Z divided by Q. This was P theta Q phi of Z given X. I mean, if you think about it, there is nothing new here, right? So uh, this was your VAE elbow, and this is your HVA elbow. The only difference that has come here is that instead of having one Z, you have Z1 to T. That's all. Yeah, quite simple, right? I mean, nothing new till now. Okay.
Yes, so notation wise, this Z1 to T refers to the Z1, Z2, Z3, and say till ZT. I mean, or is there any other interpretation of this term? Z
No,
ranging from
that's
Z
all.
to Z.
It's Z1, Z2, Z3. That's all.
Okay, fine.
Yeah. Uh, okay. Give me a second. Okay. Sorry. Right. So nothing new till now, actually. Right. Now, let us try to derive similar to what we did. Uh, Similar to what we did with, your uh, VAs. Let's try to derive a loss function so that if we want to learn theta and phi, we can do that. Okay. Let's try to do that. Okay. So let's do that. Let's do that. Okay. So let's start again with, I mean, okay, we have let's derive. Let me write it down. So derivation derivation of loss function for HVA is. Okay. Let's try to derive this thing. Let's see what it comes out to be. And this will sort of motivate us to go for diffusion models after it. Okay. Let's do that. So we have log of P of X. I mean, we have already seen that this thing is greater than or equal to what? Expectation under Q. Okay. What I will do here is, okay. So, okay, maybe, okay. Should I do that? I can just do this thing. Let me do that nonetheless. Actually, let me make some notational changes. Okay. What I'll do is, instead of calling these z's, we will call them x, not x1, x2, x3, that so on. What do I mean by that? So you have x naught, you have x1, you have x2, so on till xt. So I am instead of using z's, we will use x1, x2, x3, and our original data point x will be x naught. Okay, so this will be like p theta x1 given x naught given x1. This is your generative view, right? And similarly, there is a inference view where you have q5 x1 given x. This is just for my ease so that uh, x1 given x0. So that we won't have z's and x. We have instead we have x0, x1, x2, so on till xt. Okay. Just a change of notation here. Instead of using z's, we are using x's here. That's all. Uh, yeah. So this thing is here. So what is our elbow? Our elbow is nothing but its q of x1 to t given x naught, right? Uh, log of p x. What was this thing? It was p of x comma z1 to t, right? So it's like x naught and x1 to t. So we can write it as x0 to t. Okay. I hope this is clear that this is x is now x naught and z1 to t is x1 to t. So I'm just writing combining them and writing it as x0 to t. Okay. Divided by q x1 to t given x naught. Okay, this is just by the whatever elbow we derived here. That's all. Okay. Now let's start manipulating this term. Okay. What we are going to do is this thing will become the expectation remains as it is 1 to t given x naught, right? What we will do instead is we will start decomposing the numerator and denominator inside the log. That's all. So the first thing is pxt, the last term here, p of xt, the of prior of the generative view. Okay. And then we have what I mean, actually you can simply use this thing. We have written it already here. This thing here. Maybe I'll use so this thing, whatever we have written here, right? You can just use substitute that there. That's all. So that what will that become? So we have pxt, then we have p theta x given z1. So that will be nothing but p theta x is x naught, z1 is x1. Okay. And then we have a product here, product of p theta zt minus 1 given zt. That will be p theta xt minus 1 given xt. So this is now a product of t equal to 1 to capital T. This is p theta of x minus 1 given xt, right? Okay. Now what about the denominator? The denominator is our inference view. So for inference view, again, we have written this decomposition here, right? So this decomposition that we have here, we can directly use it. So what is it? This is q phi z1 given x, right? It's q phi z1 given x. Uh, Actually, you can just write everything in terms of xt here. So let me write it down. So this thing is nothing but product of q xt given xt minus 1, right? Because here all xt's, x2 for example depends only on x1. So I mean according to this distribution it's zt given zt minus 1, so it will become xt given xt minus 1. You have a z1 given x, this is nothing but x1 given x naught. So I'm just clubbing all of these things inside, right? So this thing will also go from t equal to 1. uh, so this thing should go t equal to 2, right? So this thing, yeah, this is how it will look like. Okay. Okay. So we have written this thing down. Any doubts still here? If you have, maybe you can ask right now. Okay. Note.
So, yes, I could not understand
Yeah.
this. I mean, you replace this Q from that orange color, I mean orange shaded formula.
Yeah.
This one.
Yeah, yeah. Yes, yes.
So, yeah. So
So
how did we?
this is just what?
Yeah, please continue. Yeah. So how did we get another term in the numerator then? Uh,
No, so there is no new term actually. So this was, so if you think about it, this is nothing but like Q phi. What is it? Q phi x1, because z1s are now x1. Okay, z's are now x's. So and x is x naught, right? Then there is a product t equal to 2 to capital T Q phi zt. So zt is nothing but now xt, right? So this is xt given xt minus 1, right? That is all. So I
yes.
can club these two, and this thing, this term and this product can be complement. The product will go from t equal to 1 to capital T. This will become q phi xt given xt minus 1. That's all. Now you can think
Yes.
about it, right? So t equal, so this is nothing but this whole expression, but for t equal to 1. So t
Right.
equal to 1 is x1 given x naught. I'm just, so you can pull this term inside this product, and that is what I have written here,
Right.
right? So once you have this term, what you can do is, uh, okay, now let's write down, okay, so what we will do is we will do a slight manipulation here. Uh, yeah, let's do that. Right, so let's do that. So let's, what I'm going to do is I'm going to change the, I mean, you will see it's nothing much, it's simple thing. So this q x1 to t given x naught, okay? And there's a log here. This p of xt, okay, p of xt and p theta of x naught given p theta x naught given x1, okay. And there is a, so what I'm going to do is I'm going to start the indexing from, instead of starting from t equal to 2, I will be starting from t equal to 1, and I will, instead of taking it to capital T, I will stop it at t minus 1, okay. So to do this change, my index inside will change, right? So I have basically, so I will write it down. Maybe if you understand it directly, tell me, otherwise I'll explain it. Does this make sense? So what I have done here is, instead of using t minus 1 given t, I am using t given t plus 1. So it's like I'm increase, so it's like substituting t minus 1 to t. I mean, if you see t minus 1 to be equal to t dash, this is t dash. Okay. And because of that substitution, this thing will become, so now like t minus 1 is equal to some dummy t dash, right? So if your t is equal to 2, what will be t dash? So this will be 2 minus 1, which will become 1. And that is what I have done here. Does that make sense? It's like you're writing the same thing, but your indexes have changed by 1. That's all.
Yes. Yes.
Okay. Uh, if that is clear, then this should also become clear. Uh, in the denominator, I am going to take out one term from here, the last term. It will be q of x capital T given x capital T minus 1, right? And the product will now go to t equal to 1 to t minus 1. This will be q of xt given x t minus 1, right? Makes sense, right? Does this make sense?
Yes, because you have explicitly pulled out this term QXT by
Yes.
XT minus 1 outside this product. Yeah, right.
Yeah. Yeah, that's all. Yeah, once you do this thing, uh, now you can actually do some trickeries. What is it? So let's do those things. So first is you have, so I will break this thing in two parts. Okay. The first part will be this thing, which will involve this thing divided by this thing. Okay. this part, and there will be another part which will involve the other remaining terms. This part divided by this part. Okay. Let's break that down. So x1 to t given x naught, this will be log of p of xt p theta of x naught given x1 divided by q of x capital T given x capital T minus 1. Okay. Plus log of product of. So now since I mean the whole point of making this in changes in index was so that the product the product range of index here and here becomes same so that I can write it as one single product. Okay. So this thing is nothing but uh, what it will be p theta xt given xt plus 1 divided by q of xt given xt minus 1. Uh, Let me know if there is any doubt. So I have basically clubbed these terms term by term, right? I mean, like you can think that t equal to one term, whatever is here, you write it down as one thing and then take the product similarly.
Yeah, I hope that there is no violation of the logarithmic, properties here. That in the numerator we have a product, in the denominator we have a product, and then
Product,
we are
yeah.
yeah, log of
Just taking,
product of.
just taking it, yeah. Yeah. So it's like just so club the ones that have same indexes here, club the with those here, right? And write them as a single term and then take the product. So it's like product divided by product is like product of multiple ratios. I mean, if that makes sense.
Yes, right, yeah, clear.
Right. So once you have written it like this, you can further simplify this thing as so you have expectation qx1 to t given x naught, right? What we will do here is we will take out this particular term, right? Which is log of p theta of x naught given x1. Okay, this is the first term. Then we have another term which is expectation of q x1 to t given x naught of log of p of xt divided by q of xp given xp minus 1. Okay, so it's like I have taken out this term and this other term and I have written it separately. And this thing will become something similar. So this is log of product which will be equal to sum of log, right? So let's write that down. So this is expectation of q x1 to p given x naught of summation over t equal to 1 to capital T minus 1 log of, so what is it? This is p theta xt given xt plus 1, right? Divided by q of xt given xt minus 1. Okay, this is how this will look like, right? Okay, now uh now you can just take this summation outside here. Okay, uh I'll write it down. So I'm writing the same thing actually. I'll just copy something just to save some time. This is how do I copy? So this is equal to this thing plus the summation comes out. Okay, this is summation over t equal to 1 to capital T minus 1 expectation under q x 1 to t given x naught of log of p theta of xt given xt plus 1 divided by q of xt given xt minus 1. Okay. Okay. Now, if you see that, all these expectations are under x1 to t given x naught. But I mean, the quantity inside here doesn't require all the latent variables, right? This only depends on x naught and x1. So what you can do is you can take out the unnecessary uh, random variables from this distribution and just ignore them. So what we can write this thing as is, so for example, the first expectation, the quantity inside depends only on x naught and x1, right? So what you can do is you can take the expectation with respect to q of x1 given x naught. All the other things will be, you can ignore them because those things don't depend on whatever is inside. Log p theta of x naught given x1. Okay. Similarly, the second term here, this thing only depends on xt and xt minus 1, right? So you can similarly do something like q of xt comma xt minus 1 given x naught, and other things are irrelevant. You can just remove them. Log of p of xt divided by q of xt given xt minus 1. And similarly, the third term here is a summation over t equal to 1 to capital T minus 1. This thing only depends on what? Xt plus 1 and xt 1 and xt minus 1. Okay. So we can do something similar here. So can just take expectation under q of uh, xt minus 1, xt and xt plus 1 given x naught of log of p theta xt given xt plus 1 divided by q of xt given xt minus 1, right? So it's just like, I mean, removing the unrequired or not necessary random variables, that's all. One last thing to do here, I mean, just last thing that we need to do here to make this thing even more cleaner, so to say. First term remains as it is. So this is q of x1 given x naught log of p theta x naught given x1. That's fine. Okay. What about the second term? The second term, what I will do is I will split the expectation in two terms. So this is expectation under uh, the first term will be, so q of uh, uh, okay. What I can do is, so I will write it down and then I'll explain. Okay, so this is q of xt minus 1 given x naught and expectation of q of x xt given xt minus 1 of log of p of xt divided by q of xt given xt minus 1. Okay, so how did I write this thing down? So you can think about it like this, right? So what did we have earlier? We had q of xt comma xt minus 1 given x1. So this was q of, oh, I'll use another color, q of x, what was it? Xt minus 1. This xt comma xt minus 1 given x naught, right? What you can write this thing down is, this thing is nothing but q of what? Xt given xt minus 1 comma x naught into q of xt minus 1 comma x naught. This is just I'm writing, so this is like writing p of x comma y is equal to p of x given y into p of y. So I'm writing it like that. Uh, is that clear? This is like x, this is like y.
Yes, yes.
Yeah. So now, because of the PGM that we have, we know that xt only depends on xt minus 1. Given, I mean, given xt minus 1, it is independent of x naught. So you can write this thing as xt given x, uh, wait, yeah, so this is actually xt minus 1 given x naught. So this is nothing but q of xt given xt minus 1 and q of xt minus 1 given x naught. So I have just written it like that. So it splits in two expectation, one with respect to this distribution and another with respect to this distribution, right? I will use a
So,
similar argument. Yeah,
so I mean, this change in the second term, I mean, probably is incorrect, I guess. So, just P of xy is fine. So, what is x is
mm,
xt and y
mm,
is it is fine here. I understood. Yeah,
mm,
that was fine.
yeah,
So, I mean,
yeah,
these simplifications are okay. Yeah.
yeah. So uh, and the third term, similarly, we can write it down as plus x. Yeah, so plus expectation under. So I want to again write something similar what we did with the second term. So I want to take out q of xt given xt minus 1, right? For that, what we will do is we will simply write this thing as q of xt minus 1 comma xt plus 1 given x naught and expectation of q of xt given xt minus 1 xt given xt minus 1, okay, of log of p theta of xt given xt plus 1 divided by q of xt given xt minus, sorry, xt minus 1. Okay. Again, how did we write this thing down? Can do something similar. So the original distribution was what? Q of xt minus 1, xt plus 1 given x naught. So the original distribution was q of xt minus 1, xt, xt plus 1 given x naught, right? What you can write this thing down is as follows. So this is q of xt given xt minus 1, xt plus 1, comma x naught into q of xt minus 1, comma xt plus 1 given x naught, right? So these two variables are like y now. Okay, and this is like x. So is a p of x comma y. This is like p of x comma y, which is equal to p of x given y into p of y. Okay. Now again using a similar argument, because this is Markovian, you can write this thing as q of xt given xt minus 1, q of xt minus 1, comma xt plus 1 given x naught. Okay. And that is why it splits into these two expectations. Now, having obtained these terms, now something should click. Whenever you have expectation and log with each other, you should always think about one thing, that is the K divergence. You think about it. If I take a negative sign outside, this thing will go up, this thing will come down, and you will have expectation under qxt given xt minus 1 log of qxt given xt minus 1 divided by p of xt. That is nothing but KL divergence between q of xt given xt minus 1 and p of xt, right? Maybe I'll write it down so that it becomes clear. So the first term is unchanged, q, it's still q of x1 given x naught log of p theta of x naught given x1 minus, because I am changing the order in the inside the log, so minus expectation, there's an expectation always q of xt minus 1 given x naught of whatever is inside will become Kale divergence between q of xt given xt minus 1 and uh, p of xt, right? And the third term will again become there's an expectation, there's an expectation under uh, q of xt minus 1 comma xt plus 1 given x naught of dkl between what is inside q of xt given xt minus 1 and p theta of xt given xt plus 1. Okay. Uh, is this step clear? I have just taken a negative sign outside so that the ratio inside the log inverts, and then I can write it down as Kale divergence.
Yes, yes.
Okay. So yeah, that's it. That's all the thing that we had to do. Now let's analyze each of these terms and see what they represent. Okay. So the first thing here, this term here, is quite similar to what we had in VAE. This is nothing but your reconstruction term again, right? It's like you obtain x1 from x naught, right? It's like obtain x1 from x naught and then again get x naught from x1. So it's similar to VAE that you want to reconstruct x naught starting from x naught. But you have an intermediate latent which is x1, the first latent that you had. Okay. So the first latent that you had. So this it's like reconstruction term on this VAE. Okay. So this looks something like that. So this is like a reconstruction term. Maybe I'll write it down. So this is like the reconstruction term. Okay. Now let's look at the term. So this term. Let's look at this term, right? So this term, what does this thing look like? So this is like the prior matching or the regularization term, right? So what is this thing saying? This thing is actually saying telling you that well at the last step, right? Whatever is your prior p of xt, which so this is the prior of your generative view, right? That should match the distribution of q of xt given xt minus 1. So it's like in your inference view, whatever is the latent variable, the last latent variable that you obtain, that should be similar that should be same in distribution as the prior of the generative view. This is similar to again the regularization term that you saw in your VAE, the normal VAE, right? So this is like your prior matching term, prior matching term, and there is a last term, this term, which is of the our interest. So this thing is actually something interesting. I'll tell you why this is interesting. This is what we call as consistency term. Consistency term. So let's look at this. What is this term saying? This is actually interesting. So you have xt minus 1, right? Xt minus 1. Then you have xt, and then you have xt plus 1. Okay. What is this thing saying? You go from in the generative view, you go in this direction, right? This is p theta of xt given xt plus 1. Okay. And then there is a inference view, which is like this. And here your distribution is q of xt given xt minus 1. Do you see what this term is doing? Actually, this term is saying that, well, the distribution at xt, when you are actually coming from this side or this side should be the same. That is what this thing is saying. It's like it is saying that at xt your distribution should be consistent. This distribution p theta xt given xt minus 1 should be equal to q of xt given xt minus 1. So at xt the distribution should be consistent. That is what this is saying. Does that make sense?
Yes, and except that, yeah. So we have xt plus 1 in the with p and then xt minus 1 with q,
Yeah.
and which makes sense. Yes. So I have a query here that do we make any assumption about the distributions q and p, like
So till now there
normalities?
is so there is till now there is no assumption. This is very generic thing. So this is hierarchical ways that we are talking about. Uh, and there is no assumption that we have taken till now. There is nothing here.
Okay, okay, fine.
Till now there is nothing, right? So yeah, these are the three terms that we needed. However, there is one problem. There's just one problem here with this formulation. And that problem is that this expectation here, right? This expectation here is with respect to two random variables, xt minus 1 and xt plus 1. Okay, you can see that, right? Uh, the problem here is that when you approximate this expectation, you will take some Monte Carlo estimate, right? I mean, what you will do is you will sample two random variables, xt minus 1 and xt plus 1, okay, for every time step, okay? And the problem here is that usually when there are more than one random variable involved in your expectation, the variance of your Monte Carlo estimate actually could be potentially high. Okay. And that too for each time step. You are doing this for each time step. Oh, I think I forgot that summation, right? There is a summation outside here. There is a summation outside here. There is a summation outside here. So basically what I'm trying to say here is that when you have two random variables that you want to sample and then take the Monte Carlo estimate of an expectation, and that too over multiple time steps, over all the time steps actually, this thing will become this expectation itself becomes very it becomes a high variance estimate. Okay. And that leads to like your learning algorithm then becomes unstable and results in like like you will see that your losses blows up to nan values and so on and so forth. Those problems come in. So that is the problem with this formulation, that there the expectation. So maybe I'll write it down. So what is the problem? The problem here is as follows. Uh, optimizing optimizing the elbow optimizing the elbow using uh, uh, using two random variables two random variables. Uh, what are the two random variables? These are xt minus 1 and xt plus 1, right? This for every time step, for every time step uh, leads to higher, leads to potentially high variance of its Monte Carlo estimate. Okay. This is the problem. And what is okay? How much time is done? Okay, so little above 30 minutes. So, and this is the problem that is solved using yet another formulation of hierarchical VAs that we will see. And from there, we will sort of switch to diffusion models. So there is one more. So basically, okay, what is the story till now? Story till now here is that, okay, we had VAs. Okay. From VAs, we want to go to a more generic framework, which is that of hierarchical VAs. Okay. Now, hierarchical VAs, did everything, we derived everything. However, I mean, these steps, in fact, are very similar to those of VAs. Okay, there is not much difference there, except a few manipulations here and there. There's not a lot of difference. So eventually, we landed to a loss function, which we can use. However, the problem is that this using this loss directly will make your learning algorithm a little unstable, and we want to avoid that thing. So what we want is basically here we want expectation with respect to just one random variable instead of two random variables. That's all, and we will see how we can do that. And once we do that, we will immediately put some assumptions on our hierarchical VAs. Okay, we will put some assumption on our hierarchical VA, this structure, so that our forward and backward. So I mean, putting those assumptions will basically lead to diffusion models, and we'll see that the diffusion models are nothing but a special case of hierarchical VAs, where the inference view, this view, is nothing but just a noising process where you are just adding some noise at each time step. And the reverse process is nothing but a denoising process where you start from a noise and you steadily denoise it and eventually land onto a uh, given data point, a particular data point. So, so this is what is remaining. So, what are the things to do? The first thing is to solve this problem, okay? And the second thing is to put some assumptions on your hierarchical view so that it becomes diffusion model. Okay. So that is where we are headed right now. Okay. Uh, so maybe if you have any question, you can ask. Otherwise, tomorrow we'll have another lecture where we will discuss those things. Yeah.
Yes, so I mean, can you give some example or some illustration of this thing that if we have multiple random variables, then it is difficult to compute the uh, value of the expectation, and we'll have to go for the Monte Carlo thing.
So
Or
no,
you can,
it's not difficult to like get the value of this expectation. It's just that so we can never calculate this expectation in closed form. I mean, I hope you will agree that we don't know these distributions beforehand. Like what we can do is we can get the samples and use a Monte Carlo estimate to estimate this expectation.
right, right,
So
right. So, so I was looking for some reference to this thing, or some video or some illustration, some example, or wherein this thing is being illustrated.
actually the reference actually is in the paper itself. So if you look at the diffusion model paper, right, the variational diffusion model paper, they have this explanation that this leads to a high variance estimate. You can use that as a reference if you want. I think
Okay,
they have some visual results as well in that paper. Yeah.
okay, okay. I hope you are talking about this paper. And then, would you be
Maybe I'll share the paper.
this one or something else?
Let me see. Yeah, you can. So this is the notes that I was referring to. Yeah, this you can use this thing, or maybe I can. Yeah, you can also look at this paper, right?
Okay, okay, yes.
Mhm.
And would you be completely covering this note which you mentioned today in tomorrow's lecture?
So, the diffusion model parts, yes, I will be covering it from this and some other resources. Okay. And
Okay,
once that is done, I will switch to score-based models, which won't be from this text. I'll use something else for that.
okay, fine. Thank you so very
Yeah.
much.
Yeah. So we'll have a lecture tomorrow, maybe. I'll put the link and then yeah, we can continue from there.
Sure,
Okay.
sure.
Thank you. Thank you. Okay.
Thanks. Bye.
Bye.